Let's take a high-level look at digital images. We'll take a look at their structure, format, and compression. Digital images are produced by a digitalization process, and we'll define that as a process of translating an analog image into a digital format, analog being what we have in our physical real world. Another term that we'll want to be familiar with is that of pixel. A pixel is the smallest accessible piece of a digital image. It's the dot or the square that takes on a certain color. All of those pixels then together make up the picture. Pixel is derived from a contraction of the words picture element, shortened to pix element, and then pixel. As I mentioned, pictures in a digital format are made up of rows and columns of pixels. The more pixels we have compressed into a small space, the higher quality the image is going to be. You'll notice in the upper right, there's a picture of the cat, and there's a small portion that has been zoomed in, and in the enlarged zoomed in area, you can see the rows and columns that are making up the image. When in the zoomed in area, we can see individual squares of different shades of white and gray, but we don't notice that in the original because the pixels are small enough. When we reference individual pixels in a digital image, we reference them as an x and y coordinate, not unlike you might have learned in math. For our purposes, the top left pixel is always going to be at x0, y0, and thus 0, 0 would be its coordinates. The next pixel in the top row to the right of the top left one would be at x1, y0, and thus 1, 0 would be the coordinates for it. Another term to learn is that of matrix. A matrix is a general term for any two-dimensional list, such as our rows and columns in a digital image. And lastly, understand that each pixel takes on a color by having a combination of red, green, and blue components. It can have none of those. That is, the values of red, green, and blue can all be at 0, in which case the color is black. If they're all turned on full value at 255, then the color that we see is white, and various colors in between. There's another video that will talk more about the mixing of the colors. But for our purposes now, just know that every pixel has a red, green, blue value that ranges between 0 and 255, because each color component is represented by 1 byte or 8 bits, and 8 bits has a maximum value of 255. We also need to take a look at the concept of compression. A digital picture has lots of pixels that make up the digital representation of the picture, and so compression is typically applied to it to reduce the size of the file that is storing all of these pixel bits of information. We have two broad categories of compression. One is called lossless and the other is lossy. There's positives and negatives about both of them. The lossless compression is a reversible compression. That is, we can take a file, compress it, uncompress it, and we'll have exactly the same thing back as we started with. That is to say, there's no data loss. However, the compression rates in lossless compression tend to be less than what we have in the lossy compression algorithms. Looking at the lossy, it's sort of just the reverse. Lossy compression algorithms are not reversible. We can take a file and compress it, and if we uncompress it, we will get an approximation, but not exactly the same file back. How much compression has been applied to it will determine how close that approximation is. It may be close enough that we don't notice it, or it may be drastically different. But it'll never be exactly the same thing we started with. And thus there is data lost in the process of the compression. But because we're able to lose some of that data, it does mean that we can have higher compression rates, and therefore the files will be typically smaller with a lossy compression algorithm than with a lossless. Another aspect that we'll take a look at is the format of how the data bits that make up the representations of the pixels are stored. We're not going to dig into the nuts and bolts of exactly how these formats all work, but just some high-level information about these four different image formats. The first one being the bitmap. It's also referred to as raster or BMP. This is an uncompressed format that is therefore a lossless storage of the data. By definition, if it's uncompressed, it's not going to lose any data. In the case of graphics interchange format, or GIF or GIF, depending on how you want to pronounce it, there's a discussion there. This format is compressed and it's lossless. So it is a reversible process where we can get exactly the same data back. The Joint Photographic Expert Group, or JPEG, is probably one you're most familiar with. This is also a compressed format, but it is lossy. Portable Network Graphics, PNG, is a compressed format, but it is lossless. So out of these four, as a rule, the JPEG will produce the smallest images, but do note that it is lossy and therefore not fully reversible. And lastly, we'll talk briefly about image resolution. The idea here is the size of the pixel, or how many pixels there are in a certain space, will determine how good the image is. Look at this in a couple different ways. If we keep the same number of pixels, but make the pixels smaller, then we will have a smaller image. Because the pixels take up less space, they'll be closer together. And that will appear to be a better quality image. Because the dots of color are smaller, our eyes tend to merge them together. On the other hand, if we take the same number of pixels and make those pixels bigger, we will end up with a bigger image, but the quality will appear worse because we're seeing bigger blocks of color that are all the same. Another way of looking at this, however, is if we make the pixels smaller but increase the number of them, then the picture size may well stay the same, but we'd still have the better quality image. And conversely, if we decrease the number of pixels but make the pixels bigger so that the picture ends up being the same size, it will be noticeably worse quality. Then we have the term pixelation that relates to all of this. If we look in the top right, we'll have an example of an image of a monitor and keyboard and mouse. And you'll notice there's a section of that image that we've zoomed in on. The original image looks decent quality, but as we zoom in, we see that what we would refer to as the pixelation, the stair steps or the blockiness of the image. And that's because we're seeing bigger blocks of all the same color. Perhaps we're seeing individual pixels or a series of pixels that are all the same color. And because pixels are arranged in rows and columns, we see the stair step sort of effect. We can see the same sort of thing with an example of resolution and pixelation in the example at the bottom with the letter R. If we start on the far right, where it's got the 100 by 100, what it's indicating there is in a fixed amount of space, we have 100 by 100 pixels. And we have a high quality picture of an R there. If we keep the picture the same size, but reduce it to 50 by 50 pixels, we've in essence made the pixels twice as big in both dimensions, because the same size, but only half as many. It's still a good quality, but we can start noticing some fuzziness around the edges of the R. And as we progress across the 20 by 20, the 10 by 10, we can still recognize the shape of the R, but because we're keeping these images the same size, the pixels or the blocks of color are much larger, and so it very much looks blocky. When we get down to 5 by 5, we've pretty much lost the image of the R, although there's variation of color. 2 by 2 is down to 4 colors, with each block taking up 1/4 of the space. And if we go to the extreme of 1 by 1, there's only one very large pixel, if you will, that's all one color. And obviously there's no way to recognize the letter R in those last couple. Just some examples of different ways of playing with resolution, pixelation, in terms of how many pixels we have in a fixed amount of space. will determine the quality of the image. We'll see you in class.